Do I know? Okay, I hope you can see it.
Yes, that's clear. Thanks.
Yeah, so thanks for organizing the workshop and thanks for inviting us. So I want to talk today about our recent work on efficient neural causal discovery without acyclicity constraints. This was joint work with Taco Cohen from Qualcomm AI Research and Evstrathios Gavis from the University of Amsterdam. To first start a bit, I want to give a background what this work is on about, and it is about causal structural learning or causal discovery in general. So from observational and interventional data, we want to find the directed acyclic graph that represents the causal structures in our data. So in other words, it's basically if we have here a set of nodes, we want to find the directed acyclic graph from those. There has been, of course, a lot of work on it. We have heard it also before today. The one we focus on here are the new trend of continuous optimization for score-based methods. So the idea is there basically to use gradient-based methods to now search the space, this huge space of possible graphs. And the common method there is basically to say, okay, we have an adjacency matrix and we parameterize it with independent probabilities per edge. So each edge has an independent probability, and we want to optimize them towards the correct causal graph. The main problem and also the main work in that area is actually about how can we limit the search space to acyclic graphs. So because if we have now independent edge probabilities, there's nothing holding us back to actually have a cyclic graph form. There are currently two main approaches. One of them is to use constraint-based optimization. So a very popular approach there is to use this constraint down here, which is basically the trace of a matrix exponential of our adjacency matrix. And if this equation holds, we can show that our graph is actually acyclic. To do this, then we basically optimize our model on the normal score function and would have this constraint on the side. However, this method is slow because we always have to wait until we optimize and converge, and then we increase basically this constraint bit by bit. And therefore, it's also hyperparameter sensitive because the steps we take, if we take them too high, then we cannot get probably the correct graph. The alternative that is often used is regularization. So that's the simpler way to just say, okay, in our score function, we simply penalize cyclic graphs. Therefore, we want to try then to get acyclic graphs. However, here you can also see it's hyperparameter sensitive because depending on the regularization rate I said, we might converge to the correct graph or not. And there are also limited guarantees actually to give. Therefore, we come to the question, is there a way where we can use these gradient-based methods to reliably perform causal discovery and also on a large scale? Because especially with constraint-based optimization for large graphs, this is too slow actually to do. To now give a more of a scope where we look at, so as said before, we try to find a DAG from observational and interventional data, and we don't constrain ourselves to certain variables, so they can be discrete, continuous, or even mixed. But in our experiments, we usually focus on categorical variables. For now, we assume also that the causal graphical model is causally sufficient, so that we don't have latent confounders, but we will discuss later actually how we can extend the method to latent confounders. Finally, the strongest assumption is about the interventions, because we want to have a setting where we can actually, in theory, show that we should be able to find the causal graph. However, even in practice, we see that even we should be able to find the graph, we often don't find them with continuous optimization methods. And the assumptions we take for them is that we say we have sparse interventions, so that only a single variable is intervened on. They are perfect, so we don't have any dependencies on the original parents, and they are available for all observable variables. So this is a bit strong for in practice, but under this setting, we should be able to actually find the graph. The method that we propose for that, we call it ENCO for efficient neural causal discovery. And it uses an idea that has been already used a couple of times before, namely the one of independent mechanisms. So basically what we do is we learn distributions from observational data and then test them how they generalize to interventional data. because we know if we do a sparse intervention on a single variable, then on the two causal graph, we only change one mechanism. But if we have a graph that has the same observational distribution, but different mechanisms, then we would actually have to change more than one mechanism. And that will show us in the interventional data because it does not generalize as well. The main idea of this approach, or the main trick, is actually that we change the parameterization of the graph. So what we do, we don't just have a big adjacency matrix with probabilities, but we add now orientation parameters. So on the right here, you can see the gamma parameters are basically a probability whether an edge exists or not. So gamma 1D is for x1 to xd, but we add this parameter theta, which is a probability in which direction this causal relationship would be. Therefore, the probability of an edge becomes now the product of the sigma of gamma and the sigma of theta. Therefore, only in one direction we can have a causal graph. And thereby the thetas are asymmetric, so that only basically in one orientation a connection can exist. The benefits of this two-variable parameterization is that on the one hand, we get more control over the gradient updates because we can now choose what is actually relevant for the orientation and what just whether there is a causal relation or not. And what we can show later is that we don't need any constraint or regularization actually for acyclicity. So just with this setting and with our assumptions on the interventions, we can already show that it converges to the correct acyclic graph. Also from our parameterization and our score function, we don't necessarily enforce acyclicity. Now let's go a bit into detail how this method works. As said before, we learn basically the distributions from observational data, which we call here distribution fitting. And we then generalize this to interventional data to learn the parameters of a graph, which we call graph fitting. For the distribution fitting, we basically then have one neural network per variable, which learns when, for example, here P of x1. And we simulate then different conditional sets. So what we basically have here is kind of an input dropout. So sometimes we show x2, sometimes not, to then learn actually multiple conditional sets. On the right, then we learn these edge and orientation parameters using these distributions here. And we will also detail more how this graph fitting works. First, we can look also a bit more on the objectives. So on the left here, the distribution fitting looks complicated, but in the end, it's just negative log likelihood. So we try to optimize the neural networks to optimize their likelihood with a mask of their input. So that's the input dropout, what I mentioned. And that is then sampled based on the probability of the edge, which is basically from our graph parameters here. So over the progress of the training, we focus then more on the training of these networks on the likely parent sets. On the right, we have here the score function, which we will use to optimize our graph parameters. And it has two also usual components. So the first one is just the log likelihood of the variables in our graph. So we basically have the expectation over the variable to intervene, the data of this intervention, and our graphs according to our probability. And these are then just log likelihoods. And the second term here is a regularizer just for the sparsity. So that's something you see in most score-based approaches, just to prefer sparse graphs basically over densely connected ones, because if two variables are conditionally independent, we want to remove this edge. And that's basically what this regularizer is for. However, you can see that we don't have any regularizer or similar on acyclicity. So it would also work here with cycle graphs. Now let's go a bit more specific to the graph fitting stage. So as I said before, we basically have expectation over interventions, over data batch, and then our graphs. So this is basically the input here. At each stage, you can imagine we have now an intervention sampled and its batch. And what we do then first is to sample a set of graphs. So for example, from our current probabilities here, we just sample 3 graphs. And there's no need actually to have acyclic graphs. So we can, for example, here sample a graph which has a cycle in. From these three graphs, we then calculate the likelihood estimates for all the variables based on our data batch here, and then summarize them in a certain way, namely that we summarize the log likelihood estimate for x2, given that there is an edge from x1 to x2, and those graphs where we do not have an edge from x1 to x2. So we simply average these two, and the same we do for the edge from xd to x2. And these log likelihood estimates we can use then to actually determine the gradients for our parameters and then update our parameters. We can now go a bit into more detail. How do these gradient estimators look like? The gradient estimator is already, so you can derive it from the score function that we have showed before in an unbiased way. And it has basically these components that we have seen before. So just as an example, these are the gradients for the edge existence parameters. And we first have here this expectation over graph, so over graph samples and over the data. So for example, over the interventional data. What we then have here is this difference of the likelihood terms. So how much better in terms of likelihood are we if we include the edge from xi to xj compared to if we do not have this edge in? This you can already intuitively explain. If under interventions an edge is beneficial for a likelihood estimate, we will likely also want to have it in our graph. For example, for independent nodes, this difference should be close to 0. And then the sparsity regularizer helps here to actually push the edge towards 0 so that we move it afterwards. So basically to summarize what that gradient estimator actually is, it's just we sample and evaluate k-graphs and look from these graphs whether having an edge is beneficial or not. I mentioned up here that our estimator is low variance. Low variance in the sense that if we compare to previous approaches that used usually a weighted reinforced gradient estimator, we can actually show that our has a 10 times lower standard deviation than the previous one. And you can imagine that this gradient variance is actually really important if you go to very large graphs, because you might not be able to sample a lot of graphs for the computational power. And therefore, it's really beneficial to have this low variance here. We can use a similar idea for the orientation parameters with one difference, namely that we don't update them on all interventions, but actually only on interventions on adjacent nodes. So what I mean with that is if we now optimize theta ij, we only update it if we intervene on xi or xj, and not if we intervene on any other nodes. This is because from these two nodes, if we intervene on them, we can definitely say which orientation actually the causal relation should be. Well, if we intervene on other nodes, we might be able to take some information, but we can't say for certain. And we have seen that actually, if we have a large graph, this would introduce way more noise and degrade the performance. And therefore, if we just focus on the adjacent nodes, can actually get very efficient gradient estimators with even lower variance here. Just to give you an intuition, how does it look like if we learn a causal graph? On the left, we have here an example graph with 13 nodes with then randomly sampled edges. And on the right, you can see the progress of how the algorithm learns the causal graph. So in the beginning, basically, it starts with all of the edges have the same probability. So this is shown all basically gray edges. And then over time progresses, the edges that are in the true causal graph become more and more likely. So basically, they get darker here. And all the other edges go to 0 and are basically removed. Therefore, you see that basically if we train it for a few iterations, that at some point we can just take a simple threshold. If an edge has a likelihood higher than 0.5, then we will include it in our prediction, otherwise not. A nice thing about the algorithm is also compared to, for example, visualization approaches, that we can give theoretical guarantees under which this algorithm converges to the true causal graph. Here, I just want to focus on the main conditions that are also in practice relevant. We have to focus here on basically for every edge that is in the true causal graph, we have two conditions. One, namely that if we intervene on the parent, so here on the xi, then having this edge should not, to xj, basically should not be disadvantaged when estimating xj for the log likelihood. That first might seem intuitive. However, there are some situations where you can show this might not be true. So in this example graph down here, if, for example, x2 is almost deterministic with respect to x1, and x2 has a very low impact on xj, then if we do not sample the edge from x1 to xj, actually x2 informs us more about x1. And therefore, intervening on x2 might lead to a difficult optimization. The second condition that we have is, well, based on our sparsity regularizer, namely that every edge must have a higher impact in terms of log likelihood than the sparsity regularizer. So that's a bit intuitive. If we would set this regularizer to infinity, then we get always an empty graph. But if we set it to a lower value, then we can actually also find the causal edges. If we have a very low sparsity regularizer, we might just need a longer optimization time. Therefore, we have this trade-off of lower sparsity regulars and more edges, but probably more computation time. However, what I also want to emphasize is that if these conditions are not fulfilled, it doesn't mean that we cannot find the graph. It just means that now local minima exist for theta and gamma. So therefore, it can be that we converge to a graph which is not the correct causal graph, but still in many cases, even if the conditions don't hold, we still find the graph. The final part of the method that I want to review here is that we can extend it to latent confounders, specifically to confounders that are over two observed variables. So if here XL is our latent confounder, that we have over two variables, XI and XJ, that currently don't have a direct causal relation. This actually causes a unique pattern in our parameters, specifically in the gamma parameters, namely that if we intervene on XI or XJ, then the edge is not beneficial between these two, because we actually then cut this edge to the latent confounder. But if we intervene on any other variables, then these two are correlated, so that edges again become beneficial. And this is not the case for any other situation. We can use that by simply now defining a score function that takes this pattern into account. So basically that we just observe the gradients for gammas for interventions on other variables and on the adjacent variables separately, and simply look at a score if that pattern is matched or not. And if the score goes to 1, then we can actually say that Xi and Xj share confounding. We will show that also in experiments, how that works. Talking about experiments, so we first start with some synthetic graphs to also generate different graph forms and actually to see what are the weaknesses of this approach and how does it compare to related approaches. So we started with a graph size of 25 nodes and measured in structural Hamming distance. So meaning if we predict a graph, how many edges do we predict too much, too less, and how many of them are wrongly orientated. We use therefore also various common graph structures. For instance, we have a chain where we just have kind of a chain as a graph structure. The fully connected graph is then the graph with the most edges while still being acyclic. A collider has one variable where all the others are its parents. And finally, a random graph where basically we randomly generate the adjacency matrix. We compare the approach here to two classical score-based approaches and two continuous optimization approaches. More specifically, SDI is an approach that uses a regularizer for enforcing acyclicity, and DCDI uses constraint-based optimization. If we compare to our approach, we actually see that ours is able to recover 5 out of the 6 graph structures without any mistakes and also reliable compared to the others. The only graph where it bit struggles is at the full graph, also because that's actually the hardest to find certain relations because the causal effect can be here very low. For instance, also DCDI, the constraint-based optimization, we see it works very well on the collider, because on the collider we can actually switch all the edges or the orientation for all edges without causing a cycle in the graph. While for the other graphs, we noticed that it still converged to acyclic graphs, but incorrectly oriented graphs. So this was now on 25 nodes. What happens if we actually scale it now to 100 or even 1,000 nodes? For this, we took now again our synthetic graphs, our random synthetic graphs, and scaled it up to 1,000 nodes and compared the continuous optimization approaches with the same computational resources. And if we compare it, so as we predicted before, the constraint-based optimization approach with DCDI does not really scale well and also runs out of memory for the 1,000 nodes, while the regularization-based one works a bit better, but even here makes a lot of mistakes in the end. Our approach in the end makes actually less than one mistake for the 1,000 nodes. So in 10 experiments there, we only noticed that two edges were missing, maybe also because of the too low sparsity equalizer. This was now on on synthetic graphs, but how about we go now to more real-world inspired graphs that we can take from the Bayesian network learning repository. So there are some popular graphs, such as the cancer graphs, which I think is very popular. And compared to the synthetic ones we tested on before, we here also have deterministic variables, or also very rare events that might be hard to detect. If we test our approach now here on various graphs and various graphs sizes, see that we still maintain mostly a perfect reconstruction. For example, the graph alarm, there we could actually show that indeed our sparsity equalizer was just too high. And if we would have chosen it 10 times or 20 times lower, we could have detected it, but we would have needed much longer training time to actually find it. The diabetes graph, for example, here has a lot of deterministic variables. We see that the regularization-based approach then fails, while ours is still relatively good in predicting the edges. The final experiment that I want to review here is for the latent confounders. So we basically picked again our synthetic random graphs with the 25 nodes from before. And we now just add 5 additional latent confounders. We just basically add 5 nodes that we randomly pick 2 nodes to have as a child or children, and then basically remove from our data set afterwards. And the goal is then to detect these latent confounders without actually hurting any of the other graph reconstruction. And if we compare here on the left, so the SHD, which is basically for observed edges, we see that we still are able to reconstruct it perfectly. And we have about 95% of the confounders can be found. However, those that cannot be found actually turn out to just be ignored because the correlation from this confounder between its 2 children is so low that it's rather removed by the sparsity equalizer than actually coming up. On the right here, we can also show how it's actually this score function that we proposed in terms of the 2 confounders compared to any other pairs in the graph. There we see that really for any other pairs, it goes to 0, while for the confounders, it usually goes to 1. And therefore, choosing this threshold to say this is a confounder or not is rather any value between 0 and 1. This brings me also then to the conclusion. So in this talk, we introduced the method ENCO for finding causal relations from observational and interventional data. Some main characteristics are basically that the score function is now unconstrained in terms of acyclicity, and that really helps to scale it in both data set and graph size. The nice thing is also that we can still give guarantees for finding the correct graph. And from the experiments, we can also see that it still holds quite well in practice. For future work, so of course, our assumptions on the interventions are quite strong, and therefore it would be nice to also extend it to imperfect or incomplete intervention sets. One aspect that could really help there is to encode transitivity, namely that right now the orientation parameters are all independent, but we know, for example, if we have a chain from 2 orientations, we also know what actually x1 to x3 would be oriented. And that is a bit harder to encode, which would be nice to have as a future work. Our code is also available public on GitHub. And yeah, that concludes my talk. Thank you for listening, and I'm happy to take any questions.
Thank you so much, Philip. That was great. Yeah, there are a few questions, but I had a quick question myself. I was wondering if you can talk about the sample size in your experiments and if you played with them and what the situation was with that.
Yeah, do you mean sample size in terms of graph or sample size in terms of interventional observational data?
In terms of the data.
The data. Yeah, that's a good point. So we tried actually with less data first, and especially for this full graph in our experiment here, it turned out that we then find wrong graphs. Actually, all of the methods were starting to find incorrect graphs, and therefore we decided rather to go with more data that we can say, okay, we can actually find it. And therefore we use per intervention. We assumed that we have 4,000 samples. And for observational, we said we have 100,000 samples, just to basically make sure that we can find the graph from this data.
Okay, Stefan has two questions for you. It's on the Q&A. I'll read it out loud, and Stefan, if you have follow-ups, please speak up. So the first question is about the experiment, and they're wondering if you can motivate or explain the embedding dimensions of the MLPs. So far, it seems you set the embedding size to 4, and they want to know how and where you determine that 4 is the optimal dimension for the embedding.
Yeah, so the embedding dimension is really a hyperparameter that we set depending on, well, our computational resources. So if we set it higher, then usually, of course, it makes more sense and is probably computationally stronger. But we have seen that kind of 4 or lower number is actually sufficient to model it well. If we probably go to now, for example, we had categorical variables of 10 possible values. We now have something like 100 or 1,000 possible values, then 4 is not sufficient. So then we would really have to scale it up.
Okay, and the other question they had was, do you assume that the target of the intervention is known?
Yes, that's a very good point. Indeed, we assume for now that the target of the intervention is known. That is specifically used in our graph fitting stage, where we say for the intervened variable, we do not update the parameters. There has been work to show that could be also used here to identify the intervention target just from the interventional data. So this way we could also get around from knowing the interventional target, but those are of course less accurate than actually knowing the target. So for now, we basically stick with assuming we know the target. Okay,
so I'll switch to a live Q&A. Thomas has a question.
Yeah, so two quick questions. Maybe I missed this. So are you assuming that you have access to interventional data on every individual variable? And the second question was, when you're learning these full conditional distributions, presumably it's possible that they could be, that they might not be consistent, so they might not fit together to be an overall joint distribution. So those are my questions.
Yeah, good point. So the first one, yes, we assume that we have interventional data for all the observational variables. That is probably future work to extend it to incomplete sets where we don't have it for all variables. The second one, yes, that's a good point. So especially if we sample the graphs, it might not hold that we actually have a valid joint distribution, simply if we have cycles in it. But we noticed, especially if we train it, it doesn't really matter that much because the probabilities for each variables are independent, kind of in the sense that each of them has a different neural network and different parameters for the edge orientations and edge existence. And therefore, we didn't really see that there's any problem if we sample them there. And in the end, if we, of course, converge to the correct graph, then it hopefully should be a correct joint distribution.
Great. There is another question from Enrico. How was the data generated in slide 9?
Slide 9, yes. So the data we usually generated where we use prior work for generating the synthetic graphs. So we took, for this specifically, we took just 12 variables, randomly generated with binary adjacency metrics. And then for each of the variables, we took a neural network and randomly initialized it. And we initialized it in that way that it creates random distributions that are still beyond uniform, but also not too peaked. So for this, we basically just looked at what previous work has done for generating these synthetic graphs. So we are not specializing our approach to just these graphs.
Okay, great. We have time for one more question. It's in the chat from Nino. Is there any reason why the edge existence is modeled using two independent factors and not as one, since you also model the direction of the edge as a separate parameter?
Yes, that is a very good question. And indeed, we also first thought it would be more intuitive to have one parameter. However, if, for example, we have the true causal connection from x1 to x3, it doesn't mean that if we intervene on x3, the edge towards x1 would be beneficial. Simply because there's a correlation on observational data, but on interventional data, that is not the case. And what can happen is actually that you get this gradient conflict. So kind of this gamma parameter then in one direction would want to go to 1, and in the other direction it would want to go to 0. And if we separate them in two separate variables, then it's much easier to optimize, and you can also then give the guarantees, because otherwise if you actually have a single variable, then you cannot give the guarantees anymore.
Awesome. Thank you so much, Philip.
Thanks.
Yes, we now move on to our next speaker, Andrea Radnitsky. Andrea, please share your screen.